Hi, do you hear me?
Yes, we can hear you.
Yes, I hear you very well.
Okay, so not all participants are present. Not all of participants of my session are attending, right?
We are seven participants actually.
Uh, I have five speakers, and just two of them are found, right?
Dear Chair,
Okay.
please start the first speaker. And
Okay, I will start. Uh, Good afternoon, everybody. I'm Shadi Khmaisi from Jordan. The first speaker of this session is Associate Professor Dr. Suraya Gomri. She is from Saudi Arabia. The title of her invited presentation is Implementation of Hydrogen Energy in Saudi Arabia and Asia, Current Status and Future Prospects. About Dr. Suraya, Dr. Suraya is Associate Professor of Physics at College of Science at Al Faisal University. She is a member of the advisory board of Al Faisal University Center for Research and Consultancy Studies. She is the chair of research committee at the College of Science at Al Faisal University. She is a member of Life Science Program Council, NCAA and ABET accreditation, and she finished her PhD at 2004 from France. The title of her dissertation was Contribution to Study the Optical Images Formation in Near Field Microscopy, Two-Dimensional Study of the Probe. Dr. Suraya Gomri has several publications in international journals, and she is editor in several journals, from which she is editor in Open Physics from 2008, and she is a member of advisory editorial board of the journal Computational Condensed Matter at Elsevier. Now, Dr. Suraya Gomri, you can start.
Thank you so much, Dr. Shadia. So I will share my screen, my presentation. Just go up. Just start from the beginning. Up. So I might stop the video because sometimes, you know, with internet, with Zoom sometimes, or you want me to keep the video?
It is good if you share your screen. It is good.
You see my screen, yeah?
Yeah, I see.
Okay, خلاص, good. Thank you so much. So, first of all, thank you for the nice introduction, Dr. Shadia. It's pleasure to be here. And I wish to also thank Professor Yasmin and Dr. and Professor Engin, my collaborators in Turkey. So it's a pleasure to be here. So actually, I was thinking to present like more precise talk, but I wanted to share with you things about the implementation of hydrogen energy in Saudi Arabia mainly, maybe not Asia today because of the limited time, 20 minutes, and share with you the current status and in research, in development, and also the implementation. So before that, I have prepared a quick introduction about myself. I'm not Saudi, and actually I'm working in Saudi Arabia. I'm French and Algerian researcher. So I have been in many countries, Europe, US, and I discovered Saudi Arabia in 2010 when I was working in KAUST, and you know KAUST now is still in with the research and development. And actually, I am in Al Faisal University, the second, I will say, university here in Saudi Arabia in matter of ranking, and the first smart Arab university and young university. So I am associate professor in physics. I have a lot of research I define myself as physicist and computational material scientist, and I have a lot of research in energies since 2010, mainly solar energy and also hydrogen materials for storage. So actually, I will give a brief introduction here about things, what is happening in Saudi Arabia and the Gulf region in general. And actually, I think we have people and we need to admit them, participant. So I will give introduction about the energy, the renewable energies in Saudi Arabia, source of hydrogen production actually here. Then I will go to technical, let's say, development about the harnessing energy from H2, mainly the hydrogen fuel cells. We have some advantages and challenges actually in the implementation. And if I have time, I will share some recent work on hydrogen systems. So actually, Saudi Arabia is well known by the oil production. And actually, I will just reduce this window because I cannot see my presentation. Yeah, now I can see it. So actually, the energy here in Saudi Arabia, the main one, as you know, it's the oil and gas. Here I'm giving a brief, let's say, an overview about the most important oil exploitation in Saudi Arabia. It's everywhere in the Arabian Gulf, around Saudi Arabia. Yani actually, it's all the Gulf region. And actually, Saudi Arabia was like not only basing, I mean, actually since now maybe 20, 25 years, not basing all the interest on oil, but also expanding and extending their research and development to renewable energies, because actually for many reasons. The most important one is the population growth. So here I'm giving an example of what is the status of the population in Saudi Arabia. And actually they are consuming a huge amount of electricity and energies. And actually with the anticipated numbers and statistics, we realize, Saudi Arabia is realizing that maybe we have to move to more types of energies and also renewable and green for commercial. So actually here, if you see this, I will take my pointer. So mainly the electricity is used in governmental buildings like schools, hospitals, commercial one, residential, and actually this residential is growing because the population is also growing. The industrial also is okay, sorry. Agriculture, the agriculture is maybe limited because it's desert country, but it still have now developing a lot of agriculture activities. Now, if we compare the consumption here in the Gulf region, and actually if I want to introduce the Gulf region, mainly Emirates, Qatar, Kuwait countries, you see KSA is the most important, the biggest consumer of energy due to the populations compared to other countries, and the biggest, of course, area here. So Saudi Arabia benefit from substantial hydrocarbon reserve, but actually also it's exporting oil over the world. And actually it was like in 2010 here, let me just like go, okay. In 2010, it was like the second ranked in oil production after Russia, and especially for the petroleum liquid. And actually around in Saudi Arabia, if we want to situate it as oil production country, it's 1/5 world oil capital is located in Saudi Arabia. So besides this, and actually this is also ongoing research and development, we discovered in Saudi Arabia we have a lot of gas reserves, and actually gas is also important as oil. Mainly, actually the most producer country here in Gulf is Qatar, after Russia, of course. But despite the huge resources and these fossil resources and fuel, Saudi Arabia has started like investing in a lot of renewable energies. And here I'm giving an example about a map, I mean, a statistic on the energies we're having now, actually renewable and non-renewable. So actually wind, we discovered a zone, a region, a very nice region in it's called Dumat Al Jindal, so it's in Arabic, and actually it has wind, and actually they are installing a lot of let's say harnessing for wind and producing electricity from it. Solar energy is well installed, and actually we have here in Riyadh, for example, I am in the capital, we have two universities where maybe 80% from their energy and electricity is provided from solar energy, like Princess Nora University and another university like King Saud, the biggest one. And actually they are also targeting to exploit nuclear energy, because as I told you, they want to focus on producing electricity with these new renewable energies and export oil, because actually the economy is based on this. So I actually, as any country, they have developed different targets. Maybe here in Saudi Arabia, people heard about the Vision 2030, where the economy of the country, not only maybe the economy, but the culture, the tourism, all sectors of important economical sectors, they are having a huge development. And actually, I am in this, let's say, I'm living this experience of transformation and transition in Saudi Arabia since 2010. And actually we are targeting in Saudi Arabia to have like to produce more let's say megawatts of energy based on solar and wind, because they are the most important one. And if we can also produce with hydrogen energy, which will be our target here in this lecture. And actually this is initially what we have. This is the revised one. So actually since 5 years target, and actually in 2030 we are looking for these numbers. Maybe we will exceed them, because actually we have a lot of development in manufacturing and optimizations. And actually there is a new city called Neom. It's not far from Jordan, and Jordan actually as a country, and Egypt also. So it's really located in the Red Sea, and it is growing in, it is like a test city for implementing renewable energies. In solar energy, where I'm working, and actually it's my, maybe now the main topic in research. If you compare Saudi Arabia actually to other countries, and actually it's in good position compared maybe to other countries, like they are behind. Uh, uh, Maybe some other countries, like for example, if I take Iran, or some countries in Africa, they still um, working or using or investing, or for example here Libya, they still counting on the oil and production. So we have investment, and as I told you, started earlier, and renewable energies and sustainable resources have recently been marked as a major key here in the vision of 2030, and actually it's implemented. What I can say also, actually Saudi Arabia is also going to renewable energies, not only because for production of electricity, but actually also for to participate in the limitation or reduction of the greenhouse effect. As you know, with the global warming, the pollution is increasing, and actually as fundamental country producing oil and petroleum products, it's very important to participate. And I think Saudi Arabia is leading this role in greenhouse reduction since few years now by implementing renewable energies like solar energy and wind energy. So actually, if we talk about renewable energies, I know the definition is really trivial actually for anyone here. Is like to look for natural resources and they are renewable, they don't expand, and actually to use them in a green manner. So in Saudi Arabia, we have here wind, as I told you, solar, sun here. The exposure to the sun is really one of the most important countries in the world, I think, receiving the radiation. Despite we have some problems with the dust and the high temperature, mainly in the summer. Now, actually, if I can tell you, we are reaching 45, 48 degrees. Last week, we reached 50 degrees in Riyadh, and actually in some other zones like Hassa. Kuwait remained the most hottest country, though, I mean, in the zone, in the region. Actually, solar energy is growing, okay? So it's more likely here 25% from the renewable energies we are exploring in Saudi Arabia are from solar. We have also geothermal, and actually I was like, as a professor, I'm teaching a course called Renewable Energies, and I was always looking to find a way to, let's say, sensibilize the student on the energies, mainly the Saudi students, our future engineers and doctors here, on the importance of renewable energies. And I discovered that also geothermal is growing. Hydropower, instead we don't have, and actually Saudi Arabia has like, it has two sources of water, Red Sea and the Gulf Arabian Sea, and also biofuels, actually biofuels, sorry. And biofuels, maybe because it's desertic country and zones, but they still have resources, 20%, and wind, as I told you, maybe 10%. So actually, a lot of projects, and actually, if you see here in this map or histogram, it is showing the hydroelectricity. So actually, you see here, this is, as I told you, the wind and solar. They are always actually implementing or making hybrid renewable energies systems like solar and the wind here. And actually, as I told you, the solar is everywhere. The wind maybe is limited to this zone, but actually it's really one of the biggest one. And actually, they started producing electricities in really important cities like Jeddah, Al-Khafji there is actually zero. Actually, you see here zero because Al-Khafji is is the biggest oil production, I will say, central, and other systems here. I mean, other resources, and Yanbu, for example, etc. So this is the market actually by 2019. And actually, these are the recent numbers about how the market, and actually we have also business behind all these renewable energies, and the market is growing on solar energy, wind actually, and the other energies are mainly the let's say the hydrogen and nuclear one. The nuclear stage still actually in early stage, like discussion of implementation and collaboration with other countries. But here we will talk about the hydrogen since it is the topic of this Congress. So I'd like to give you information about the hydrogen energies. Now it's growing everywhere. We're over the world, and actually worldwide, we are producing 70 million metric tons of hydrogen. And actually it is generated by steam methane reforming and coal gasification. We have some amount, and actually limited application maybe from electrolysis. So it remains a challenging production, energy production now, and especially to make it producing and delivering electricity with high efficiencies. So actually, the current, if we have some estimation here, the current cost per kilogram of hydrogen is around $6-8. This is a recent estimation, which actually remain reasonable, because actually compared to the let's say the barrel, oil barrel now, or petroleum barrel produced like $72, I think, per today. So it is really less expensive compared to oil. However, this can, I would say this cost can vary and depend on the process. So, because actually the process is not the same, is not standard, we have a lot of process and we will discuss them here on the generation of the hydrogen and techniques. So, actually, if I want to say here about Saudi Arabia, actually we started working on hydrogen energies. I want to give you just the market here about the hydrogen energy and how it's growing. And actually here E is the estimation, for example, by 2019 and 2020. P here is the projected for 2024, of course. So you see the market is increasing actually linearly, and it is very important because the techniques of production are also improved by all the research we're having. And actually, I can give you here an example of actually the status of production in developed countries like North America, of course, Europe and Asia. The other countries, we don't have numbers. They're still in a stage of research and development and testing. Of course, it's a matter of strategy in a country when we switch to a new energy. But we have in different countries, and I'm aware, and actually in Algeria, I know that people are working on hydrogen energy since a while, mainly in maybe fundamental research, but actually it's still very important to advance this. And actually in Asia, for example, here, the market is really huge compared to Europe and maybe even North America. And globally, actually, this is what we are producing in megawatt. And what we are expecting in 2030, maybe we don't have estimation yet, but Europe, and actually you see here we have really for Europe, they want to switch from 84 megawatt to 10,000 megawatts. You know, Europe, they don't have any resources. They have maybe, natural resources like oil, and they still depend on gas from Russia and oil from other countries like Saudi Arabia and the Gulf zone. So this is why we see in Europe a lot of development in renewable energies. They are pioneer in solar energy like Germany. And now they want to be the pioneers in hydrogen energy production. And actually, when you produce your energy, you are just powerful country. So implementation in KSA, I told you, and actually KSA, even, and actually they have, people are estimating when the oil would expire. You can never know when it expires because they still discover a lot of resources now. And actually, as I told you, since I'm here, and actually it's my 10th year in Saudi Arabia, I'm facing all this transition and in economic development, and mainly here we have a new city called Neom, and actually there it's a city of all renewable energies. So they are targeting to produce the energy not from oil, but only from solar energy and hydrogen energy. So they started the implementation. It is working. It's really working as in actually hydrogen energy. And we have recently in there is a city called Dhahran, and Dhahran is well known by the oil production also. It's in the east of Saudi Arabia. And they have Dhahran Techno Valley. It's related to one of the universities, but actually it's one of the plans and actually to develop renewable energies. They launched a new hydrocarbon-based hydrogen system for fuel cells vehicles. So it is Toyota who started first. Now other companies are coming like Mercedes, Hyundai, and Honda. They are well established here. So this is one of the first cars with hydrogen fuel cells. So actually, the cost of the oil, and I would say the benzene actually is still less expensive in Saudi Arabia, but actually, as I told you, it is matter of strategy at let's say mid-term and long-term. So the current production actually over the world, how we can produce this hydrogen energy, which is, by the way, clean and green and very friendly for the environment. But still very dangerous, and we will see this at the end. And actually, we have a lot of resources from chemicals, mainly here, they are trying for chemicals. Coal, for example, we don't have so much here in Saudi Arabia. Nuclear one, I told you it's under installation. Renewable sources, and this is what we will see here, and maybe natural gases. So we have two ways, green and blue, and actually depending on the technique. If it's from, for example, the blue, it's from steam reforming, and actually both of them, they are linked to each other, and actually dependent also on the cities where we have. So actually, I have summarized here three principles or three methods that we are trying to test in experimental labs here, and mainly in KAUST and King Saud universities, and our university where we are working also in lithium batteries. It's another topic, but we're still in production of electricity without oil. So actually, for hydrogen production via electrolysis, we have two main mechanisms here. So it's like we are producing hydrogen and oxygen at the same time. If I can summarize it here without going in deeply in technical details, maybe if we have questions. Actually, we have these three equations where oxygen evolution reaction, what we call OER, and hydrogen evolution reaction, HER, it's electrochemical reaction that takes place in cathode here. And actually, I have summarized this like there is like membrane between them, which will allow, let's say, separation between these two molecules. And actually, with electrolysis, it's still actually a very limited technique, because the efficiency of production is 16%. Let's say 16% may be what is expected, maybe, but theoretically it's around 10-20%. And if I go to the thermochemical one, where actually I'm trying to understand it with experimental collaborators by working on different hydrides. And actually, this technique is uses actually the phenomena of H2 or water splitting at high temperatures. And actually, it is actually, it works, and actually the efficiency is around 40-56% when it is estimated theoretically. We always overestimate theoretically efficiencies regarding this conversion. And actually, from my side, I'm working on different oxides. Now, sorry, Dr. Shadia?
5 minutes remained.
How many?
5 minutes.
Okay, I will go speed. So the third technique is PEC, and it is also summarized here based on photovoltaic, let's say, or photocatalysis phenomena, where light is actually intervening in the splitting of water and then separating H2. Now, actually, harnessing energy from H2 need also storage system, and they are called hydrogen fuel cells. I know it's a huge topic. I'm discovering it with my collaborator, experimental one. And actually, we have different principle here on how it works. I can summarize it, but actually, if since I'm working actually with experimental as a computational material scientist, we can see that, for example, lithium batteries or lithium polymers and fuel cells, if you compare here the weight and actually how it is harnessing, how it is the storage, of course, the fuel cells still limited in their capacity of storage. So this is one thing. And actually, what I can say also, they're still green, and this is the most important thing, and actually renewable. So it's like yani, actually with this conversion we still have we still producing hydrogen, oxygen, and we need water and also energy production here. Since I have only 5 years, I want to give you more details. So I will go. So how it works? It's everywhere. Yani actually, the fuel cells. It's really simple principle as any batteries. It's matter of let's say transportation between electrons and anodes, and actually. The fuel, which is here H2, hydrogen, is transported to anode of the cell. Then it undergoes a reaction, and this reaction, what we call anode reaction, splits the fuel into H plus, which are protons, so charges, and electrons, and we will take these electrons and we use them to produce electricity. So actually, okay, we're producing hydrogen, we're having 3 methods, and they are theoretically now the estimation we want to reach 83%. And actually, the story is like we are not reaching it. We are maybe around 60 and 70%. It's from business point of view, I will say, it's not maybe attractive at this moment, because when you compare it to other renewable energies, maybe solar systems where we are reaching now 42% with different compounds, silicon, amorphous, perovskite. Maybe perovskite is still limited because as new systems. And this is because we have so much losses, ohmic losses, and actually we cannot control them. It is when you compare it also to the batteries, and lithium batteries, now we are using them in our smartphones, and now actually we have electric cars, and it's still actually more sustainable, more actually in storage of energy compared to the fuel and hydrogen. And actually the story is like when you see the advantage and disadvantage, maybe the most important one is the hydrogen energy is green, emission is free, it is available in infinite quantities, and actually in space, in our universe, 73% is hydrogen.
Just 1 minute.
Yeah, okay, so yeah, I'm arriving to the conclusion. And hydrogen energy, I started working on it and actually from maybe fundamental point of view, where I'm working using density functional theory, where we are exploring fundamental properties of alloys based on hydrogen. And actually the purpose now is not only to study them, like see the fundamental properties, their ability to store hydrogen, especially the estimation of the storage capacities. This is what we did in last 2 papers published this year. And the story now is to go beyond 1, 2, 3 compounds, but do what we call now machine learning, which is based on artificial intelligence, in order to have an assessment of different compounds before, let's say, we start actually interested experimentally to any model. So I wish to finish with this picture. So this is the wind energy, and actually it's going on here, some references maybe. And so thank you so much for giving me this opportunity to deliver my talk. As I told you, I didn't want to go technically in calculations and results, because I know many participants and my collaborators attending from Turkey, they are working on the same topic. And I'd like, actually, I'm working with a lot of experimenters in Pakistan, India, Korea, France, Germany, and now also Ireland, in different sources of energies. And my target is not only to study fundamental things, and we want to go beyond these fundamental predictions and participate in understanding what is happening.
Thank you, Dr. Soraya.
Thank you so much, Dr. Shadi, and thank you for all the participants.
Thank you for your presentation. Okay, now, is there any question? No questions. Okay, thank you again.
Thank you so much, Dr. Shadia. Thank you.
Goodbye.
Thank you. Bye-bye.
Now we come to our next presentation. It is entitled Structural and Mechanical Properties of CSLiCOS2 compound AB initio study.
Very nice.
Is the presenter here? Dr. Okoforan Ogozan.
Yes, hi.
Please share your screen. Dr. Okozran.
Sorry, we are waiting for the video sharing about the presentation.
Yeah. I didn't see. You shared your screen?
Sorry.
Okay. Okay.
Hello, everyone. Thanks for coming. I'm Oğuzhan Okuran from Aksara University. I'm a PhD student of physics at Aksara University. What I'd like to present to you today is structural and mechanical properties of cesium lithium cobalt disulfide compound ab initio study. I'll divide my presentation into three main parts. 1. Introduction. 2. Material and methods. 3. Results. If I briefly talk about the title compound exhibits semiconductor behavior at low electrical conduction with small thermal activation energy. The layered thorium dichrome disilicium type compound shows versatile physical properties including antiferromagnetic, ferromagnetic, superconductivity, and heavy fermion. The purpose of this presentation is to examine the crystal and electronic structure, elastic and mechanical properties of the title compound with layered thorium dichrome disilicium type structure. For this purpose, the VASP program package was used for calculations based on ab initio methods. Quantum chemical calculations based on theoretical principles are called ab initio. In the ab initio method, mathematical approaches such as reducing a complex function to simpler functions are generally used. Ab initio calculations generally give very good qualitative results, and the smaller the molecule, the higher the precision of the qualitative results. The advantage of ab initio methods is that they approach a definite result when all approximations are made from a sufficiently small size. Here we briefly give the crystal information for the title compound. The title compound has a tetragonal crystal structure. Unit cell parameters A1 equals A2 and A3 are different from them. Angles are equal to each other and are 90 degrees. Atomic coordinates for the title compound are given in this slide. The table above gives a summary of the experimental crystallographic parameters for the title compounds. Here, since it is understood from the occupancy value that the 4b base coordinate is experimentally shared by nearly 50% of lithium and cobalt atoms, 6 possible different models have been proposed and calculations have been made for these 6 different models. As a result of the calculations, the models that were identical to each other were remote, and the data calculated for the 4 models were presented on the next slides. The atom coordinates of the 4 different model structures calculated and the unit cell shapes drawn with the VESTA program are given on the next slides. On this slide, the atomic coordinates of the unit cell for the Model A, are given in the table, and the unit cell shapes drawn with the help of the VESTA program are included. On this slide, the atomic coordinates of the unit cell and the unit cell shapes for the model C are given. On this slide, the atomic coordinates of the unit cell and the unit cell shapes for the model E are given. On this slide, the atomic coordinates of the unit cell and the unit cell shapes for the model F are given. Let's talk about the method we use. VASP program was used for all calculations. For the exchange correlation energy, generalized gradient approach, PBA parameterization was used. The cutoff energy was taken as 625 electron volts. A 1313 for gamma centered grid was used. The second order elastic constants were calculated using the stress-strain method. Approaches that take into account the spatial variation of density are called generalized gradient approximations. GGA has been shown to better predict bond length, and total energy for many systems. Due to the large density gradients in some materials, the GGA approaches is used instead of LDA. Density functional theory reduces the Schrödinger equation written for the n-electron systems to the n-single electron Schrödinger equation. The most important problem in the FT is that exchange correlation energy is not known. The results regarding the structural parameters are given in the slide. We have listed the structural parameters we calculated for the title compound together with the literature values in this table. The results we found are in agreement with the experimental values. In addition, the energy volume graph is drawn and given above. From the energy volume graph above, it can be seen that the energies and volumes of models A and B, C and F are close to each other and there is little distortion of each other. Here I would like to talk about the results we obtained regarding this electronic structure. Electronic band structure and state density curves of 4 different models of the title compounds are given above. In the above graphs, the electronic band structure was drawn along the high symmetry points in the first Brillouin region. The Fermi energy level was taken as 0. As can be seen from the graphics, all models of the title compound show metallic character. Some of the mechanical properties we have obtained as a result of our calculations are given here. The second order elastic constants were calculated for a single crystal using the stress-strain method and are given in the table above. We have seen that these values meet the mechanical stability conditions given for tetragonal structures. This indicates that the material is mechanically stable. Other mechanical properties are given in the slide. Here, polycrystalline elastic modulus was estimated using the second order single crystal elastic constants and given in the table. V and R stand for Voigt and Reus limits. The bulk modulus B is the ability of a regularly compressed object to resist compression. The bulk modulus was calculated using the equation of state. Shear modulus G is the resistance of the solid to this state against the sliding of the atomic planes on each other. Young modulus E, the resistance of an object under load the elongation. Poisson ratio nu gives information about the bond structure of the material. Roughly, if the Poisson ratio is around 0.1, it can be said that the covalent bond structure is dominant. And if it is around 0.3, 25, the ionic bond structure is dominant. W temperature theta d, the temperature theta d at which all atoms begin to vibrate is called W temperature. Environment transverse, longitudinal, and average sound velocities. It can be estimated from the B/G values whether it is ductile or brittle material. If this value is less than 1.72, it is brittle. If it is high, it is ductile. As can be seen, the B/G value is greater than 1.72 for A and F, so it shows ductile properties. It is less than 1.72 for C and E, which means that these models are fragile. This result is important in terms of showing that the physical characteristics of different slices of the same materials may be different. Now I would like to talk about the general results and objectives of our study. In the study, the theoretical physical properties of the tetragonal, the title compound, were investigated. It was seen that our calculation results were in agreement with the experiments. From the examined electronic bond structure of the material, all models show metallic character. It was observed that it has predominantly ionic bond structure. It was seen that the calculated second-order elastic constants met the mechanical stability conditions. From the polycrystalline elastic properties estimated using elastic constants, the material was estimated to be brittle for models A and F, and ductile for models C and E. Thank you for listening.
Thank you for your presentation.
Thank you.
Now our next presentation is entitled The Calculation of the Structural, Mechanic, Elastic and Electronic Properties of Ru4Al3B2 compound by AB initio method. The speakers are Sibyl Ozdo, Senel, Engin, Atishek, Haji Ozishek from Turkey.
Hi everyone, thanks for your participation. I'd like also thank the organizers of this meeting. My name is Sibel Özdor Şenal from Aksaray University. I am a PhD student of Physics Department. Today, I'm going to talk about the structural, mechanic, elastic, and electronic properties of ruthenium-4 aluminum boride compound. First of all, here are the subtitles of our study. I'll start off brief introduction. After, I'm going to talk about calculation methods. And finally, I'm going to give the results of our study. Turner borides have some intrinsic properties such as high melting point, high hardness, high corrosion resistance, and high electrical conductivity. Also, for their great potential as a wear-resistant material, they have attracted scientists' attention in recent years. The aim of this study is to examine the structural, electronic, and mechanical properties of the Turner boride compound ruthenium-4 aluminum boride. All calculations were carried out using the Vienna ab initio simulation package. For the generalized gradient approximation exchange correlation energy, the Perdev-Berg and Zerhoff parameterizations were used. The eigenstates were expanded into plane wave basis functions, and the ion cores were represented with the pulp pseudopotentials. The kinetic energy cutoff was set at 400 electron volts. 6 by 6 by 13 gamma-centered K-point grid were used to sample the beryllium zone. Here, basic crystallographic information is given for ruthenium, aluminum, boron, which is also the first input data for the calculations. The compound has tetragonal geometry. This information taken from experimental study which is given below. The ruthenium-4 aluminum boride compound crystallizes in a tetragonal structure and contains 18 atoms in the unit cell. Structural parameters and literature values calculated for this compound are given in the table. The calculated structural parameters well agree with experimental values reasonably well. In addition, the energy volume curve was plotted and the bulk modulus and derivative were calculated using the equation of state. It can be said that this material has a hard character. The derivative of the bulk modulus is a measure of isotropy and is an experimental parameter. Since the applied pressure in calculations is isotropic, it's expected to be around 4. It's also possible to predict the pressure volume variation from the energy volume with data. For this material, it seems that the volume decreases almost linearly with pressure. The electronic band structure was plotted along the high symmetry directions of the first beryllium zone, and the Fermi energy level was taken as 0. There appears to be no band gap. It suggests that the compound is metallic in nature. As can be seen from the graphics, the ruthenium-4 aluminum boride compound shows conductive character. And also density of states curves were plotted. The low number of density of states at the Fermi energy level indicates that the material is stable. It can be said that the conductivity is predominantly provided by ruthenium elements. This graph shows which orbitals contribute to the density of states. It can be said that ruthenium-D orbitals are dominant contributors in both valence and conductivity bands. The charge density curves are given here. According to the charge density curves, the ionic bond structure is dominant in the compound. In addition, a small amount of covalent bond structure is observed. The second-order elastic constants of the ruthenium-4 aluminum boride compound were calculated by means of stress strain methods based on first principle calculations. The calculated second-order elastic constants are given here with the Born stability criteria for tetragonal structure. It has been determined that ruthenium-4 aluminum boride compound satisfies the stability conditions for tetragonal structures and is mechanically stable. Polycrystalline elastic modulus are calculated using the Voigt-Ruiz-Hill approximation. The equations are given here. In addition, Ambient sound velocities and corresponding debye temperature were calculated with equations given here. The calculated bulk modulus, shear modulus, and their ratios, Poisson's ratio, debye temperature, and sound velocities are given in the table. A material is brittle if the bulk modulus shear modulus ratio is less than 1.75 and is ductile if the ratio is higher than 1.75. For ruthenium-4 aluminum boride compound, the ratio is 1.99, so it can be said that the compound is ductile. Young's modulus could also provide a good measure of the stiffness of materials. Ruthenium-4 aluminum boride is hard nature. The typical Poisson's ratio is 0.1, 0.25, and 0.33 for covalent, ionic, and metallic materials respectively. The Poisson's ratio is 0.29 for ruthenium-4 aluminum boride, so the compound shows ionic nature. About the debye temperature, all vibrations modes are active. And last, I'd like to talk about vibrational properties. Atomic vibrations are an important predictive method for stability. The obtained Brillouin zone-centered phonon frequencies were in the positive region, indicating that the compound is dynamically stable. There are 54 atoms in supercell, 3 acoustic and 51 optic branches. It seems that ruthenium elements are dominant in the acoustic and low optic region. All elements are contribute to the mid-optic region, and upper optic vibrations are dominated by boron elements. Thanks for listening.
Dear Chair, can you turn on the microphone?
Yeah. Is there any question? No questions? Okay, so we go to the next presentation. The next presentation is entitled DFT-QE Calculations of Hydrogen Peroxide Sensitivity on Boron Graphdiene. Is BGDY an antiviral surface or not? The speaker is Aliv Sakaraya or Sirab Shintork. Any one of them here? Okay.
Hi everyone, my name is Alev Sakarya. I am PhD student at the University.
Please, the voice is very low.
Calculations on hydrogen peroxide.
The voice is very low.
Is boron graphene an antiviral surface or not? In this study, we figure out at the answer of these questions.
The voice is very low.
This is the outline of my presentation. Nanomaterials describe the materials of which a single unit small size between 1 and 100 nanometers. Materials with the structure at the nanoscale often have unique properties like optical, electronic, pharmaceutical, or mechanical properties. Generally, nanomaterials are categorized according to their dimensionality, morphology, state, and chemical composition. Carbon nanomaterials are a novel class of materials that are widely used in biomedical applications, biomedical fields, including antioxidant activity, biosensing, imaging, tissue engineering, and the cancer treatment.
Can you increase the voice? I don't hear you.
Molecular or nanotips show different chemical and physical properties, including conductivity, mechanical properties, chemical stability, and so on. Based on their dimensionality and the shape, nanomaterials can be further divided into four classes: 0, 1, 2, and 3-dimensional. As biosensor and biomedical devices have become increasingly important to everyday diagnosis and monitoring, two-dimensional materials have proven to very promising candidates for biological applications because of the high surface area, the volume ratio, and the properties of electronic and the optical. 2D materials are receiving increased interest in biomedical applications owing to their special physicochemical and surface properties. Figure shows us that how the surface of properties, how the surface properties of these materials influence their applications as biosensor and the biomedical devices. Why are we focusing on the graphene? Because graphene, one of the two-dimensional carbon allotropes with one atomic layer of carbon sheets, and in recent years, considerable efforts have been paid attention to the development of graphene for hydrogen storage and the cancer drug delivery. Our motives for the study based on the previous molecular dynamics simulations. These latest articles emphasize the important role of boron graphene. Our starting point is how we can use the surface properties of boron graphene. 2D materials have attracted considerable attention in biomedical applications due to their antimicrobial activity. Antimicrobial activities of 2D materials are related to physicochemical and structural characteristics of these materials, and also in biomedical applications of 2D materials, the biological species such as biomolecules, cells, and the tissues will be in direct contact with the surface of these materials. In this way, the successful development of biomedical devices lies in the surface properties. 2D materials have antiviral surface. Hydrogen peroxide can prevent the replication of viruses. Moreover, hydrogen peroxide is a strong oxidizing agent that has been widely used as a cleaning and a disinfectant agent. Based on these studies and based on these properties, we made a structure with hydrogen peroxide and the boron graphene. Using the DFT calculations, we investigate the capture of hydrogen peroxide on boron graphene layer. Boron graphene layer contains 14 atoms, 12 carbon, 2 boron, and hydrogen peroxide consists of 2 hydrogen and 2 oxygen atoms. We employed the quantum expressor to pattern book Erdogan-Holt generalized gradient approximation has been used for the exchange correlation, and to deal with the electron-ion core interaction, projected augmented wave method has been employed. Cutoff energy value was 45 right back. The Brillouin zone was sampled with the 331 grid, and the green D3 method was used for the van der Waals corrections. Hydrogen peroxide places on the top of the boron and the polar position at the hexagonal corner near the boron atoms. First, we isolated boron graphene and hydrogen peroxide were optimized separately, and then cluster structures are optimized. We chose two different regions because we want to see if there will be a deformation of boron graphene. As you can see from the GIF files show us during the optimization how they interact with each other. For both positions, hollow and the top position, the closest distance between the Oxygen antiboron is at for top position, which means hydrogen peroxide bonds more strictly than at the hollow position. The optimized structure, molecular structure of hydrogen peroxide bond lengths and the bond angles are listed for isolated and after interaction boron graphene. Before and after optimization, the changes of lofting charges, both hydrogen peroxide and the boron graphene are listed. Lofting charge shows the carbon atoms near the boron are negatively charged, and the hydrogen peroxide interacts with the boron graphene through the first oxygen atom of hydrogen peroxide. Absorption energy can be defined as the decreasing energy while two materials are combined under absorption process. Absorption energy at the top position is bigger than the hollow positions, so which means that to break the bonds between hydrogen peroxide and the boron graphene for the top positions needs more energy. By using the highest occupied and the lowest unoccupied level, we computed the energy gap and the Fermi energy values. In both positions, energy gap are becoming larger. The conductivity is greatly increased after placing hydrogen peroxide on the boron graphene. The absorption of hydrogen peroxide gives a significant effect on the conductivity. Density of states, projected density of states, potential energy distribution are drawn for both positions. The physicochemical properties in the frame of the Kopman's theory, Homo and Lumo energy were also used to predict ionization potential and electron affinity. Parameters such as electronegativity, global hardness, chemical properties, etc. are related to Homo and Lumo energies, so we can calculate these parameters using the following equations. These are the calculated physicochemical parameters. Besides the previous properties, it's known that recovery times gives an information about the interval of the formation process. To sum up, in this study, VFD calculations are performed to determine the electron structure properties and the dynamics of the hydrogen peroxide placed top and the hollow position on boron graphene. Negative absorption analysis suggests that the absorption process is exothermic. Interatomic distances show that hydrogen peroxide absorption through the energy atom is thermodynamically more favorable than interaction from hydrogen sites at both positions. The lofting charge analysis shows that hydrogen peroxide molecule interacts with boron graphene through oxygen molecule at both positions. The sign of energy gap shows the increase or the decrease in energy gap. We employed the absolute value of the energy gap. The response values transmitted in both configurations have spurious sensing properties in detecting hydrogen peroxide. So boron graphene may have potential application as hydrogen peroxide sensor. The calculated record times values are too short to desert of hydrogen peroxide molecule from boron graphene surfaces at room temperature. And we hope that the current theoretical work might play an important role in guiding related experiment research. Thanks for your attention.
Thank you for your presentation. Is there any question? No questions? Okay. Now we can go to the last presentation. The last presentation is entitled Highly Anisotropic Mechanical Properties of Monoclinic Ta2 NISE5 First Principles Study. The presenters Sabit Korshak and Haji Ozisik. You can start,
Good
please.
afternoon, everybody. Thanks for your participation. I would like also thank the
Please,
organizers of this
please,
meeting.
your voice is very
My name
low.
is Sabit Korcak from Architecture University.
Please increase your voice. The voice is very low, please.
Good afternoon, everybody.
It's better.
Thanks for your participation.
Slightly better.
I would like also thank the organizers
Yes, so sorry.
of this meeting.
The source file
My
is
name is Sabit
problematic
Korcak from
for
Architecture
some.
University. I'm going to talk today about highly anisotropic mechanical properties of monoclinic TA2 and ACA5.
It's good if you can increase the voice.
Assignment is a layered ternary carbonic compound. Its crystallis is monoclinic structure. Structure parameters were taken from an experimental study conducted by Larkin et al. In addition, a study by Lee et al. Showed that it is an exotonic insulator Vihar. In the lower right corner, the primitive unit cell of this structure is C. In this table, you can see the parameters of experimental structure taken from the experimental work done by Larkin et al. In the study, to investigate the structure and mechanic properties using the FT-based first principle methods. To calculate second-order elastic constants by stress-strain methods, we used a late code for 2D and 3D elastic. Other calculations were studied using is a complex package program that can perform quantum mechanics and molecular dynamic simulation. The FT, the main purpose of density functional theory, is to solve the multi-body interaction electron wave function on the base of electron density. In the study, calculations were performed using PBA parameterization in the AB initio-based generalized gradient approach. That is, parameters and structural properties were obtained as a result of energy minimization. The obtained parameters are listed in the tables together with the experimental data. We can observe that the obtained results are in agreement with the experimental data. There are 13 independent elastic constants for a monoclinic material. The second-order elastic constants of the compound were calculated by means of stress-strain methods based on first principle calculations. Polycrystalline elastic models are calculated using the Voigt-Royce-Hale approximation. It has been determined that compounds satisfy the stability conditions for monoclinic structure and it is mechanically stable. Polycrystalline elastic models was calculated with the help of the obtained elastic constants. Young's models is right to the hardness of the material. It was observed that it was not very high in these materials. According to the we can say that material have a soft character by looking at the Young models. It is seen from the position ratio that they have an ionic bond structure. From the BG ratio, it is predicted that compound is brittle. Using the second order elastic constants obtained in this study and the late interface, the three-dimensional behavior of the polycrystalline models was estimated. A high degree of orientation dependence was observed in elastic models. Young models and linear compressibility have about 30 times anisotropy, while shear models has around 43 times. Also, points ratio has highest anisotropy along the other model. It varies between 0 and 0.88 depend on the orientation. These extreme p ratios are known to be characteristics of shape memory materials. Here we could see the spatial dependence of young models. It was between 4 GPa and 110 GPa depending on the orientation. It has the highest value for 001 direction about 110 GPa. Here we could also see the spatial dependence of linear compressibility. If this value is more low, the material is harder, while it is too high, the material is soft. It has ranges from about 4 per TPA to 120 per TPA depending on the direction. The next is the spatial dependence of shear models. The green curve shows the lower limit known Rose limit and below the upper limit also known white limit. If this value is more low, the material is harder, while it is too high, the material is soft. It has ranges from about 1 GPa to 48 GPa, where the XA plane has highest anisotropy. The last anisotropy graph is for the spatial dependence of shear models. Here also the green curve shows the lower limit and below the upper limit. If this value is more low, the material is harder, while it is too high, the material is soft. It has ranges from the about 0 to 0.8 GPa, where the XB and YZ plane has highest anisotropy. AB initial simulation performed for compound in monoclinic structure. Structure results agree with oval experimental values. The compound shown semiconductor behavior and gives 0.769, a electron indirect band gap, and this also agree with the experiment. It has been observed that stress strain result provides mechanic stability. Thanks.
Thank you for this presentation. Is there any question? No questions? So we finished the last presentation and we can close this session. Thank you for the organizers. Thank you for the team in Gazifen. Thank you for the chair of the conference, Professor Yasmin. Thank you to all of you. Goodbye.